In this video, we're going to talk about Le Chatelier's principle. So Le Chatelier's principle tells us that if we apply a stress to a reaction that is at equilibrium, the reaction will go in the direction that will relieve the stress. So we're going to talk about different stresses that we can apply to a reaction and how a reaction would shift. So there are a few different types of stresses that we can apply to a reaction. One is that we can change the concentration of reactants or products. We can change the pressure or volume, particularly if we're talking about gaseous reactants and products. We can change the temperature of a reaction. And that will have an effect on some reactions. And we're going to talk about how each of these changes would affect a reaction, and the reaction is going to go in the direction that will relieve the stress that we apply to it. So for example, if we have the reaction N2 plus H2 yields NH3, which is ammonia, then if Kc is equal to Qc, then that means that we're at equilibrium. If we add some N2 to this reaction, now we've added more reactant. This reaction is no longer at equilibrium because we just increased the concentration of one of our reactants. So what's going to happen is this reaction is going to shift to the right and make more products because now we've made QC less than Kc. So we need to make more products to reestablish equilibrium. So we're going to have a greater concentration of N2, but some of that N2 that is going to have to react with H2, which means the concentration of H2 is going to decrease, and we're going to form some NH3, some ammonia, so the concentration of ammonia is going to increase. So eventually, we will establish a new equilibrium, but we have to do that by reacting some of the N2 we've added and some of the H2 that we already had to form ammonia. So when you disrupt the equilibrium by adding or removing a reactant or product, if you add a reactant or product, the reaction is going to go in a direction that consumes whatever you added. So in our example, we added N2, we added a reactant, so we had to go towards products to consume some of that reactant. So if you add a reactant or product, then the reaction is going to go in a direction that consumes whatever you added. If you remove a reactant or a product, then the reaction is going to go in a way that replenishes whatever you removed. So for example, if we had that reaction N2 plus H2 yields NH3, and then I go in and remove some of the H2, now the reaction is going to shift back towards the reactants and replace that H2 that I took out of this reaction mixture. Let's take a look at an example where we apply QC and KC and determine whether we're at equilibrium. So the question asks us, an equilibrium mixture of 0.50 molar N2, 3 molar H2, and 1.98 molar ammonia is disturbed by increasing the N2 concentration to 1.5 molar. So we originally started with 0.50 molar N2, And now we've added enough N2 so that the concentration of N2 is 1.50. So if we write our expression for QC, we have NH3 is our product, and N2 and H2 is our reactants. So we have a concentration of 1.98 molar for our ammonia, and now we have a concentration of 1.50 for our N2 and 3 molar for our H2. So if we take 1.98 squared divided by 1.50 times 3 cubed, that gives us a value of 0.0968. That's our value for QC. So QC is much less than KC. So since QC is less than KC, what's going to happen is our reactants are going to get consumed, and we're going to go towards products and form more products so that we can reach equilibrium again. So if we take another example here, we have iron plus the thiocyanate ion reacts to form iron thiocyanate. And our iron thiocyanate is a bright red color. Well, if we have our reaction mixture, which has our iron thiocyanate in it, if we add oxalic acid to our solution, this is going to react with the iron and form an iron complex. So what happens is we decrease the concentration of iron, so our reaction is going to shift back towards reactants to produce more iron. Now this reaction with iron and thiocyanate, our reactants, is colorless. So you can see in the picture where we get some of this iron complex with the oxalic acid, we end up with a more colorless solution than we had to start with. If we add mercury chloride to the solution, this mercury chloride, the mercury reacts with the thiocyanate ion and forms a complex. So we remove thiocyanate ion from our solution. So again, we move back towards the left to replenish that thiocyanate ion, and you can see we get a clear solution here. Now, what if we change the pressure or the volume? So let's go back to our reaction where we have N2 plus H2 gives us ammonia. So we have a mixture of N2, H2, and ammonia at equilibrium. And then we decrease the volume, so we increase pressure. Well, now we've got a smaller volume here. So what's going to happen is we're going to go in a direction that has the smallest number of moles because we have less space, so we want to get fewer moles of gas so that we don't need as much space. So on the reactant side, we have 1 mole of N2 and 3 moles of H2. That's a total of 4 moles of H2. On the product side, we only have 2 moles of reactant. 2 moles of product. So we have 4 moles of reactants and 2 moles of products. So if we decrease the volume and increase pressure, we're going to go towards the side that has the fewest number of moles, which is going to be our product side. So we're going to have more products in here and fewer of our reactants. So when we have an equilibrium that's disturbed by a change in pressure or a change in volume that results in a change in pressure, if we increase the pressure by reducing the volume, we're going to go in a direction that decreases the number of moles of gas. If we decrease the pressure by expanding the volume, then we're going to go in a direction that increases the number of moles of gas. So for increasing pressure, we want fewer moles of gas. If we're decreasing pressure, we want more moles of gas. So let's take a look at an example where we apply this principle. We have an equilibrium mixture of 0.50 molar N2, 3 molar H2, and 1.98 molar ammonia. And we reduce the volume by a factor of 2. So if we think back to molarity, molarity is equal to moles per liter. So if you divide the volume in half, then you're going to double the concentration because we have half as much space and the same number of moles. So if we're taking half the space with the same number of moles, then the concentration is going to be twice what it was. So if we write QC and we've written this expression earlier, so we're going to go ahead and just copy our QC expression here. So we're going to double all these concentrations. So 1.98 doubled is 3.96 squared. 0.50 doubled is 1 molar. And 3 doubled is 6 molar. So if we take 3.96 squared divided by 1 times 6 cubed, that gives us 0.0726. So again, this is less than Kc. So since Qc is less than Kc, we're going to consume reactants, and we're going to go in a direction that produces more products. So what if we have a change in temperature? So in this case, we have a reaction that has a delta H of negative 92.2 kilojoules per mole. So if we think back to thermochemistry, a negative sign means that our reaction is exothermic. So I could essentially add heat as one of my products here. Because this reaction is exothermic, it's going to release heat. So the way to deal with heat when we're trying to determine the effect of temperature is to treat heat as a reactant or a product. If the reaction is exothermic, heat is a product. If the reaction is endothermic, heat is a reactant. So we get the reaction that I just wrote there. So in this case, because heat is a product, if we increase the temperature, we're adding more heat to the right side, to our product side. So the reaction is going to shift to the left to form more reactants to reestablish equilibrium. If this were an endothermic reaction, we would go in the other direction because we would be adding a reactant. Now, keep in mind that changing the temperature changes the value of your equilibrium constant. The equilibrium constant is only true at that particular temperature that it was measured at. So let's take a look at another example. We have delta H for this reaction is positive 57.2. That means that this reaction is endothermic. So we would write this as N2O4 plus heat gives us 2NO2. So this means that if we added heat to this reaction, it would shift the equilibrium towards the right, towards the products, because we added another reactant. So to give you another example here, or actually this is the same reaction we were just talking about, NO2 is a dark brown. N2O4 is colorless. So we have this reaction ice to start with, and then we take it out and we move it to room temperature, and then we put it in a hot water bath. And you can see as we increase the temperature, we move towards products because we have to put heat in, so heat is a reactant here. Another example, we have cobalt, it's a complex, we have water molecules in here. When it's this complex, the solution is pink. When it is cobalt chloride, it's a royal blue color. So we can see as we increase the temperature, we shift this reaction towards products. So this reaction is endothermic. One of our reactants here would be heat. So as we add heat to this, we shift towards the products. Okay, so this wraps up Chatlier's principle. So we will get some more practice with this in class. So I will see you in class.